Close your eyes for a moment and imagine standing on a beach. Not just any beach, but one that exists 4 billion years ago. The waves that lap at your feet are grey-green, thick with dissolved iron and minerals that give the water an almost metallic sheen. Above you, the sky glows orange and pink, a perpetual sunset caused by methane hazes that wrap around the planet like gossamer veils. There is no grass beneath your feet, no birds calling in the distance, no insects buzzing through the warm air. The only sounds are the crash of waves, the rumble of distant volcanoes painting the horizon with pillars of ash and steam, and perhaps the hiss of hot rock meeting cold water somewhere along this alien coastline. This is Earth during the Archean Eon, a span of time so vast it challenges our ability to comprehend it. From 4,031,000,000 years ago until 2,500,000,000 years ago, our planet underwent transformations so profound that they set the stage for everything that would follow. The Archean, whose name derives from the Greek word archaeos, meaning ancient or primeval, represents the second chapter in Earth's story, following the violent Hadean Eon and preceding the quieter, more familiar Proterozoic. It is during this immense stretch of time, lasting 1.5 billion years, that Earth first became recognizably planetary in nature, rather than merely a molten sphere of rock and metal. The Archean world was a place of extremes that would seem utterly foreign to modern eyes, yet it was also the crucible in which some of the most fundamental aspects of our planet were forged. It was during these ancient days that the first true continents began to rise from a global ocean, that life took its first tentative steps from simple chemistry to complex biology, and that the stage was slowly set for the great oxygenation that would eventually transform Earth into a world capable of supporting complex organisms. Every breath you take, every piece of solid ground beneath your feet, every living thing you encounter owes its existence in some way to processes that began during the Archean Eon. What makes the Archean so fascinating and so challenging to study is that it represents a time when Earth operated under fundamentally different rules than it does today. The planet was hotter, with heat still radiating from its violent formation and from the decay of radioactive elements that were far more abundant than they are now. The atmosphere lacked free oxygen, that element so essential to most modern life, instead containing methane, carbon dioxide, and nitrogen in proportions that would be instantly lethal to any human. The continents, such as they were, existed as small islands and proto-continents, rather than the vast land masses we know today. Even the sun itself shone with only 75 to 80% of its current brightness, a dimmer star that should have left Earth frozen solid, yet somehow did not. As we journey through the Archean, we will trace the story of how this alien world gradually transformed into something more familiar. We will watch as the first solid ground emerged from endless seas, as the first living cells began to replicate and evolve, as the chemical composition of the atmosphere and oceans slowly shifted in response to both geological and biological processes. We will encounter rocks so ancient that they themselves are older than most of Earth's familiar features, formations that preserve evidence of life from a time when the very concept of life was still being defined by the universe. The Archean is divided into 4 eras, each representing a distinct phase in Earth's early development. The Archean, from 4,031,000,000 to 3,600,000,000 years ago, saw the formation of Earth's oldest preserved rocks and the possible emergence of life. The Paleo-Archean, from 3,600,000,000 to 3,200,000,000 years ago, witnessed the establishment of the first microbial ecosystems and the beginning of continental growth. The Meso-Archean, spanning 3,200,000,000 to 2,800,000,000 years ago, was marked by increasing diversity in both geological and biological realms. Finally, the Neo-Archean, from 2,800,000,000 to 2,500,000,000 years ago, saw the formation of the first supercratons and the earliest hints of the oxygen revolution that would transform the world. Throughout all these eras, the Archean Earth was a laboratory of planetary evolution, testing countless geological and biological experiments, most of which failed, but some of which succeeded spectacularly. The successes we see preserved in ancient rocks, in chemical signatures that hint at biological processes, in the very structure of Earth's oldest continents. The failures have been lost to time, eroded away, or subducted back into the mantle, leaving only tantalizing hints of what might have been. As we prepare to explore this ancient world, it is worth remembering that we are not merely studying dead rocks and abstract theories. The Archean Eon shaped everything that came after. The continents that formed then still exist at the hearts of modern land masses. The life that evolved then gave rise to every organism that has ever lived, including ourselves. The atmospheric changes that began then set the stage for the oxygen-rich air we breathe. In studying the Archean, we are studying our own deep origins, the planetary childhood that made our existence possible. So let us return to that ancient beach, to that world of grey-green seas and orange skies. Let us watch as the first continents rise, as the first living cells divide and multiply, as Earth slowly, gradually, over vast spans of time, becomes the world we know. The Archean Eon is not just ancient history. It is the foundation upon which all subsequent history was built, the beginning of a story that continues today, 4 billion years later, on a planet transformed beyond recognition, yet still carrying the indelible marks of its ancient past. The boundary between the Hadean and Archean eons, marked at approximately 4,031,000,000 years ago, represents one of the most significant transitions in Earth's history, though pinpointing exactly when or how this transition occurred remains challenging. Unlike more recent geological boundaries that can be identified by mass extinctions or dramatic environmental changes visible in the rock record, the Hadean-Archean boundary is defined primarily by the age of the oldest intact rock formations we have found. This makes it as much a boundary of our knowledge as it is a boundary of Earth's actual history. The Hadean Eon that preceded the Archean was named after Hades, the Greek underworld, and for good reason. This was a time of such intense heat and violence that no rocks from this period have survived in recognizable form on Earth's surface. What little we know about the Hadean comes from rare mineral grains, particularly zircons, that somehow endured the subsequent 4 billion years of geological tumult, and from studies of the Moon, whose cratered surface preserves a record that Earth's active geology has long since erased. The late Hadean was marked by what scientists call the Late Heavy Bombardment, a period from approximately 4,100,000,000 to 3,800,000,000 years ago, when the inner solar system experienced an intense spike in asteroid and comet impacts. This bombardment, which overlapped with the beginning of the Archean, was caused by a reorganization of the outer solar system as the giant planets migrated to their current orbits, destabilizing countless objects in the asteroid belt and beyond, and sending them careening toward the sun. Earth, along with the Moon and other inner planets, bore the brunt of this cosmic onslaught. Each impact during this period was a cataclysm. The larger impactors, some measuring 10 kilometers or more in diameter, struck with such force that they vaporized rock, created temporary lakes of molten stone hundreds of kilometers wide, and sent shockwaves reverberating through the entire planet. The heat generated by these impacts would have sterilized the surface repeatedly, boiling away any oceans that had begun to form and potentially destroying any early life that might have gained a foothold. Some scientists have argued that life could not have permanently established itself until the bombardment ended, while others suggest that life might have survived in deep ocean hydrothermal vents, protected by kilometers of water from the worst effects of surface impacts. Yet even as Earth endured this cosmic bombardment, it was also undergoing a fundamental transformation. The planet was cooling. During the Hadean, Earth had been essentially molten, or at least had a surface temperature high enough to prevent the formation of stable crust. The heat came from multiple sources: the gravitational energy released as the planet accreted from the solar nebula, the decay of short-lived radioactive isotopes far more abundant in the young solar system than today, and the heat generated when iron and other dense elements sank toward Earth's center to form the core. This last process, called differentiation, released enormous amounts of gravitational potential energy as heat, helping to maintain Earth's molten state. By the beginning of the Archean, however, these heat sources were beginning to wane. The accretion of the planet was complete, the short-lived isotopes had decayed away, and the core had finished forming. Heat was still being generated by the decay of long-lived radioactive elements like uranium, thorium, and potassium, and this internal heat was actually much greater than today. But it was no longer sufficient to maintain a completely molten surface. For the first time in Earth's history, rock could cool enough to solidify and remain solid. The formation of the first permanent crust was not a single event, but a gradual process that probably occurred in fits and starts. We can imagine small rafts of solid rock forming on the surface of a magma ocean, only to be pulled back down into the molten interior by convection currents, melted and reformed. Over time, however, as the planet continued to cool, these crustal rafts became more stable, lasting longer before being recycled. Some of them began to stick together, forming larger masses. Among the oldest rocks ever discovered are the Acasta gneiss in northwestern Canada, dated to around 4 billion years ago, and the Nouveau-Guituk greenstone belt in Quebec, with some estimates placing portions of it at 4,280 million years old, though this older age remains debated. These ancient fragments cluster around the Hadean-Archean boundary, suggesting this was when stable crust first formed in quantities that could be preserved. These oldest rocks are predominantly mafic in composition, rich in magnesium and iron, similar to modern oceanic crust, but somewhat different in detail. This suggests that the earliest Archean crust formed primarily through direct solidification of mantle-derived magmas, not through the complex processes of plate tectonics that would develop later. The crust was thin, hot, and constantly being recycled, but it was crust nonetheless, a solid shell separating the molten interior from the atmosphere and whatever water existed on the surface. The formation of stable crust had profound implications. For one thing, it meant that water could begin to accumulate on the surface rather than boiling away into space. Where this water came from remains a subject of debate. Some of it was almost certainly delivered by comets and water-rich asteroids during the late heavy bombardment, as these icy bodies vaporized upon impact and added their water to Earth's growing oceans. But some water may also have been present all along, bound up in the minerals that formed Earth during its accretion, released gradually through volcanic outgassing as the interior heated and melted. Regardless of its source, by the early Archean, Earth almost certainly had liquid water on its surface. We know this from several lines of evidence. Certain rock types found in the Archean, particularly those that form from the metamorphism of water-deposited sediments, indicate the presence of liquid water. Chemical analysis of ancient zircon crystals, some dating back to the late Hadean, shows isotopic signatures consistent with their formation in the presence of liquid water, and the very existence of certain mineral assemblages that can only form when water is present provides further confirmation. But here we encounter one of the great puzzles of early Earth history, the faint young sun paradox. Computer models of stellar evolution tell us that 4 billion years ago, the sun was only about 75 to 80% as luminous as it is today. At that reduced luminosity, and given the composition of Earth's early atmosphere, the planet should have been completely frozen, its surface temperature well below the freezing point of water. Yet the geological evidence clearly shows liquid water was present. How can we reconcile this apparent contradiction? The answer lies in the greenhouse effect. While the early Archean atmosphere lacked oxygen, it was rich in greenhouse gases that could trap heat. Carbon dioxide was almost certainly present at levels far exceeding modern concentrations, perhaps 100 to 1,000 times higher than today. Methane, an even more potent greenhouse gas, may also have been abundant, produced by early methanogenic microorganisms once life appeared. Some models even suggest that nitrous oxide, produced through abiotic chemical reactions, might have contributed to the greenhouse warming. Together, these gases created a thick thermal blanket around the planet, trapping enough heat to maintain liquid water despite the dimmer sun. This greenhouse atmosphere would have given the early Archean sky a very different appearance from today's clear blue. The high carbon dioxide levels, combined with methane and other gases, would have created hazes and given the sky various orange, pink, or brownish hues, depending on the exact atmospheric composition and the angle of sunlight. The overall effect would have been alien and beautiful, a constantly shifting display of colors that we might find stunning if we could somehow travel back to witness it. As the Archean progressed beyond its earliest stages, the late heavy bombardment gradually subsided. By 3,800 million years ago, the reign of impactors had decreased to levels more similar to today, though still higher. This meant that the surface could remain stable for longer periods, allowing geological processes to operate without constant interruption by catastrophic impacts. Continents could grow without being immediately destroyed. Sediments could accumulate in basins, and life, if it had not already appeared, now had a better chance of surviving and spreading. The transition from Hadean to Archean thus represents a shift from a planet in violent flux to one beginning to achieve a kind of rough stability. The surface was no longer molten or constantly bombarded from space. Liquid water had accumulated into oceans. A primitive crust had formed and was beginning to differentiate into protocontinents and oceanic areas. The atmosphere, while still deadly to modern organisms, had settled into a more consistent composition. Earth had graduated from planetary infancy to childhood, still changing rapidly, but no longer in danger of being completely sterilized or melted back into uniformity. Yet this early Archean world remained profoundly different from modern Earth. The continents, as we will see, were small and scattered rather than vast and connected. The oceans were hot, mineral-rich, and lacked dissolved oxygen. The atmosphere was chemically reducing rather than oxidizing. Volcanic activity was far more intense than today, and the biological world, if it existed at all in the earliest Archean, consisted solely of simple single-celled organisms lacking nuclei or any internal organization. The Archean Earth was a work in progress, a planet still figuring out what kind of world it would become. If we could somehow position ourselves above the early Archean Earth and look down at its surface, we would see a planet dominated by water to an even greater extent than today. Modern Earth is sometimes called the Blue Planet for its extensive oceans, But Archean Earth deserves the title even more. The continents that did exist were small, scattered islands and proto-continents rising from a truly global ocean. Some estimates suggest that as much as 95% or more of Earth's surface was covered by water during the early Archean, making it a genuine water world with only isolated patches of dry land. These Archean oceans were not the clear blue waters we associate with tropical seas today. Their composition was fundamentally different, shaped by the chemistry of the early atmosphere, by intense volcanic activity, and by the absence of the biological processes that now help regulate ocean chemistry. If you could somehow sample these ancient seas, you would find them rich in dissolved iron, giving the water a distinctive grey-green or even reddish tint, depending on the concentration and chemical state of the iron. Silica would have been abundant, making the water slightly more viscous than modern seawater. Various sulfur compounds, manganese, and other metals would have been present in concentrations far exceeding anything found in today's oceans. The temperature of these early oceans is a matter of ongoing debate and research. Some models suggest the Archean oceans were quite warm, perhaps averaging 40 to 50 degrees Celsius or even higher, compared to modern ocean average temperatures of about 17 degrees Celsius. This heat would have come from multiple sources: the still hot Earth's interior, which radiated more heat through the thin crust than today, volcanic activity, which was far more intense, and possibly the enhanced greenhouse effect that kept the planet from freezing despite the faint young sun. Other models, however, suggest temperatures may not have been quite so extreme, particularly after the end of the late heavy bombardment. What is certain is that these oceans had a fundamentally different chemistry from modern seas, particularly with regard to oxygen and acidity. Today's oceans are mildly alkaline and contain dissolved oxygen that supports marine life. Archean oceans were broadly reducing rather than oxidizing, meaning they contained little to no dissolved oxygen. This had profound implications for the solubility of various elements. Iron, for example, readily dissolves in oxygen-free water as ferrous iron, but quickly precipitates out in the presence of oxygen as insoluble ferric oxides. The high dissolved iron content of Archean oceans tells us that these waters were essentially anoxic throughout. The pH of early Archean oceans, their level of acidity or alkalinity, remains a subject of debate. Some researchers argue that the high carbon dioxide levels in the atmosphere would have made the oceans acidic, similar to the process of ocean acidification we observe today as atmospheric CO2 levels rise. Others suggest that the intense volcanic activity and weathering of silicate rocks would have produced enough alkaline compounds to maintain a neutral or even slightly alkaline ocean. In some models, inspired by modern soda lakes found in volcanic regions, early oceans might have had high alkalinity, high pH, and relatively low concentrations of calcium and magnesium. One of the most fascinating aspects of Archean oceans was their lack of a persistent redox cline, that layer in the modern ocean where oxygenated surface waters transition to anoxic deep waters. Today, oxygen produced by photosynthesis near the surface penetrates to various depths depending on local conditions, creating zones of different oxygen concentration. The Archean Ocean lacked this stratification for most of its history because oxygen was not being produced in significant quantities. The entire water column, from surface to seafloor, was uniformly anoxic. However, this does not mean Archean oceans were completely uniform in their chemistry. Far from it. There would have been significant horizontal and vertical variations based on factors like proximity to volcanic vents, depth, temperature, and later in the Archean, biological activity. Shallow, near-shore environments would have been quite different from deep basins. Areas near volcanic vents would have had distinctive chemistry compared to regions far from such activity. These variations created a patchwork of microenvironments, each with its own unique chemistry and potential for supporting different types of chemical or biological processes. The salinity of Archean oceans, the concentration of dissolved salts, likely differed from today's as well, though estimates vary widely. Some models suggest early oceans were less salty than today because there had been less time for salts to accumulate through weathering and volcanic input. Others propose they might have been saltier in certain areas, particularly in shallow seas, subject to intense evaporation under the cloudless Archean skies. What seems clear is that the mix of salts was different, with potentially higher concentrations of some elements like silica and iron, and possibly lower concentrations of others like sulfate. The depth of the Archean oceans is another intriguing question. Some evidence suggests these oceans were actually deeper, on average, than modern oceans, perhaps by a few hundred meters. This seems counterintuitive, since we might expect a smaller total volume of water in the early Earth. But the key factor is not total water volume, but the volume of continental crust above sea level. With smaller continents and thinner continental crust, there was less land to displace water. The ocean basins could be deeper while the continents were smaller, resulting in a net increase in average ocean depth and a planet with less exposed land. Tides in the Archean oceans would have been dramatically different from today's. The moon was much closer to Earth then, perhaps only about 60% of its current distance in the early Archean, and it has been slowly receding ever since due to tidal friction. A closer moon means stronger tidal forces, so Archean tides could have been enormous, perhaps several times the height of modern tides. In some shallow coastal areas, the tidal range might have exceeded 10 meters or more, creating vast intertidal zones that would be alternately flooded and exposed twice daily. These tidal zones may have been important sites for the origin of life or the evolution of early organisms, providing unique environments where chemistry and early biology could interact in complex ways. The temperature gradient in Archean oceans, the difference between surface and deep waters, was probably less extreme than today. Modern deep ocean waters are cold, hovering just above freezing, because they form from cold, dense water sinking near the poles. But in the warmer Archean, and possibly without ice caps at the poles, this process would have been different or absent. Deep waters would have been warmer, reducing the temperature stratification of the ocean. This more uniform temperature profile would have affected ocean circulation, with implications for nutrient distribution, heat transport, and the evolution of early marine ecosystems. Volcanic activity played a crucial role in shaping Archean ocean chemistry. Submarine volcanoes and hydrothermal vents, far more numerous and active than today, poured enormous quantities of dissolved metals, gases, and heat into the oceans. These hydrothermal systems were major sources of the iron that gives Archean oceans their distinctive character. They also provided reducing chemical compounds that could fuel early forms of metabolism, making them potentially important sites for the origin and early evolution of life. The sediments accumulating on the floors of Archean oceans were also distinctive. Without the abundant skeletal remains of marine organisms that today form limestone and other biogenic sediments, Archean marine sediments were predominantly chemical precipitates and weathered rock particles. Cherts, fine-grained sedimentary rocks composed of silica, were particularly common, forming from the direct precipitation of dissolved silica from seawater. Iron-rich sediments would accumulate in areas where chemical conditions favored the precipitation of iron minerals. And volcanic sediments, the products of underwater eruptions and the weathering of volcanic islands, were abundant. As the Archean progressed, biological processes began to influence ocean chemistry in increasingly significant ways. The evolution of photosynthesis, first in anoxygenic forms that did not produce oxygen, and later in oxygen-producing cyanobacteria, started to alter the chemical balance. Early photosynthetic organisms would have removed carbon dioxide from seawater, precipitating carbonates. They would have produced organic matter that sank to the seafloor and was buried, effectively removing carbon from the system. And eventually, they would begin producing oxygen, setting in motion a chain of events that would gradually transform the oceans from reducing to oxidizing. Though this transformation would not be complete until well after the end of the Archean. The Archean Ocean was thus a dynamic, chemically complex environment, fundamentally different from modern seas, but by no means simple or uniform. It was an ocean of iron and silica, of warmth and tides, of hydrothermal vents and volcanic islands, scattered across a vast global expanse of water. It was in this alien sea that life would take hold and begin its long journey toward the complexity and diversity we see today. Understanding these ancient oceans is crucial to understanding the emergence and early evolution of life, for the chemistry of the water shaped what kinds of metabolism were possible, what kinds of organisms could survive, and what evolutionary pressures would drive early biological innovation. Rising from the vast grey-green waters of the Archean Ocean were the first true pieces of continental crust, the ancestors of the landmasses we walk upon today. These ancient crustal nuclei, called cratons, represent some of the oldest and most stable portions of Earth's surface. They have survived billions of years of geological tumult, remaining largely intact even as mountain ranges rose and eroded, oceans opened and closed, and supercontinents assembled and broke apart multiple times. To understand Earth's Archean history is in large part to understand how these first continents formed. The word craton comes from the Greek kratos, meaning strength, and it is an apt name. A craton is a large, stable block of continental lithosphere that has maintained its integrity for hundreds of millions to billions of years. Cratons consist of two parts: the crystalline basement rocks of the crust itself, often exposed at the surface in regions called shields, and the thick, cold, strong mantle root that extends downward for 150 to 250 kilometers into Earth's interior. This deep root is key to cratonic stability. It is depleted in certain elements, making it less dense than surrounding mantle, and it is viscous and strong, resisting deformation. Archean cratons, or their remnants, exist on every continent today, though they make up only about 3% of Earth's current exposed surface area. This may seem like a small proportion, but it is misleading. Most cratons are partially or completely buried under younger sedimentary rocks that have accumulated over billions of years. The true extent of Archean crust is much larger, possibly accounting for half or more of the total continental crust by volume. We just cannot see most of it at the surface. The oldest known intact rock formations date to approximately 4,031 million years ago, right at the beginning of the Archean, but these are rare exceptions. Most preserved Archean crust is younger, with significant amounts forming between 3,800 million and 2,500 million years ago. This does not mean older crust did not exist. It almost certainly did. But the geological processes operating during the Archean were so vigorous that much early crust was destroyed. recycled back into the mantle, or metamorphosed beyond recognition? How did these first continents form? This seemingly simple question has no simple answer, and it remains one of the most actively researched topics in Earth science. The process was almost certainly different from modern continental formation, which occurs primarily through plate tectonics. Evidence for true plate tectonics in the modern sense does not appear until late in the Archean, or even early in the subsequent Proterozoic Eon. So if plate tectonics was not operating, or was operating differently, what process could generate continental crust? The prevailing model, supported by multiple lines of evidence, involves a three-stage process of crustal evolution. The first stage was the formation of a primordial mafic crust in the late Hadean and earliest Archean. This crust was similar in composition to modern oceanic crust, but much thicker, possibly forming through extensive melting of the mantle at a time when Earth's interior was significantly hotter than today. This mafic crust covered the entire planet, or most of it, providing a substrate upon which later continental processes could operate. The second stage involved the partial melting of this mafic crust to produce more evolved, silica-rich magmas. When the lower portions of thick mafic crust were buried or heated sufficiently, they would begin to melt. But unlike the direct melting of mantle that produces mafic rocks, the remelting of mafic crust in the presence of water produces a distinctive suite of rocks called TTG, standing for tonalite trondhjemite granodiorite. These rocks are more silica-rich than their mafic parents, lighter in color and less dense. TTG rocks are characteristic of Archean cratons and are found throughout the preserved Archean rock record. The formation of TTG magmas was a crucial step toward true continental crust. As these less dense, silica-rich rocks formed, they would tend to rise, accumulating into thicker masses that stood higher than the surrounding mafic crust. Over time, repeated episodes of TTG formation could build up significant volumes of proto-continental crust. This process seems to have been particularly active between 3,800 million and 3,200 million years ago, a period that saw the formation of large amounts of TTG crust in many cratons around the world. The third stage of continental formation involved further chemical differentiation and the development of true granite. Late in the Archean, particularly in the Neo-Archean era, between 2,800 million and 2,500 million years ago, large volumes of granite formed. These granites are more potassium-rich than TTG and indicate a further stage of crustal evolution. Their formation helped stabilize cratons by thickening the crust and by providing an additional source of heat-producing radioactive elements that kept the crust buoyant. But where on the planet did this crustal formation occur? And what was the structure of early Archean continents? Here we encounter another area of active research and debate. Some models propose that Archean continents formed primarily at volcanic arcs above subduction zones, much like modern continental crust. In this view, chains of volcanic islands would have formed and then aggregated together, gradually building up into larger landmasses. This model has the advantage of explaining many features of Archean rocks and is consistent with some evidence for early plate tectonic processes. Other models suggest a different mechanism involving mantle plumes, vast upwellings of hot mantle material rising from deep within Earth. When a plume reaches the base of the crust, it can cause extensive melting and volcanism. The products of this melting, initially mafic, can then be remelted to produce TTG and eventually granite. In this model, cratons form through vertical growth as magmas rise from the mantle and differentiate, rather than through horizontal accretion of volcanic arcs. This plume-driven or plume-lid tectonics may have dominated during the hotter early Archean, before transitioning to more plate-like processes later. The reality was probably some combination of these mechanisms, possibly varying from place to place and time to time. The early Archean was a time of experimentation, when Earth was testing different modes of heat loss and crustal formation. Some cratons may have formed primarily through plume processes, others through proto-subduction and arc volcanism, and still others through hybrid mechanisms that defy easy classification. Regardless of the exact formation mechanism, by the Mesoarchean and Neo-Archean, a distinctive pattern had emerged in many cratons. This pattern, visible in regions like the Wyoming Craton in North America, the Yilgarn Craton in Australia, and the Kap Vaal Craton in South Africa, consists of alternating domains of two rock types, granite gneiss complexes and greenstone belts. The granite gneiss complexes are exactly what they sound like. Large regions dominated by granitic rocks and gneiss, a metamorphosed rock with characteristic banding. These regions represent the stabilized, differentiated continental crust. Between and around these granite gneiss domains are the greenstone belts, linear to arcuate zones filled with metamorphosed volcanic and sedimentary rocks. The volcanic rocks in greenstone belts include basalts, similar to modern volcanic rocks, but also komatiites, a distinctive ultramafic rock type that requires temperatures exceeding 1600 degrees Celsius to form and is almost never seen in younger rocks. The sedimentary rocks include turbidites, deep water deposits transported by submarine landslides, as well as cherts, banded iron formations, and various other rock types. This granite greenstone pattern suggests a dynamic environment where volcanic activity was building up new crust, even as granitic magmas were intruding and older rocks were being metamorphosed. The greenstone belts may represent ancient oceanic crust that was somehow trapped between growing continental masses, or they may be remnants of intracontinental rift zones where the crust was being stretched and thinned. The debate continues, but what is clear is that this distinctive geological architecture is characteristic of Archean cratons and different from the structure of younger continental crust. As the Archean progressed, these individual crustal blocks and protocontinents began to collide and amalgamate. By the late Archean, around 2,700,000,000 years ago, some researchers argue that the first true supercraton, called Superior or Knorrland, may have formed through the assembly of multiple cratons. This supercraton would have included parts of what are now North America, Greenland, and parts of Europe and other land masses. If it existed, it would represent the first time significant amounts of Earth's continental crust were gathered into a single large landmass. The formation of cratons had profound implications beyond just creating land. Thick continental crust is buoyant, standing high and resisting recycling back into the mantle. This means cratons could serve as platforms for sediment accumulation, creating shallow seas and coastal environments that would become important for the evolution of life. The weathering of continental rocks provides nutrients like phosphorus and trace metals that are essential for biology. And the formation of cratons required the removal of incompatible elements from the mantle, changing the chemical composition of both the crust and the mantle in ways that would affect all subsequent geological processes. Today, when we examine the oldest parts of continents, we are looking at the survivors of the Archean craton formation process. These ancient crustal fragments, some 4 billion years old, have witnessed the entire subsequent history of Earth. They have been pushed together and pulled apart multiple times as supercontinents formed and broke up. They have been buried under younger rocks and then exhumed by erosion. They have hosted the evolution of life from single cells to complexity. Yet through it all, they have remained largely intact, testimony to the stability that makes them cratons. In studying Archean cratons, we are not just examining old rocks. We are investigating the process by which Earth became a planet, with continents, with land rising above the sea. This transformation from a water world to a planet with substantial land masses was essential for the subsequent evolution of both the planet and the life upon it. Without continents, there would be no weathering cycles to regulate atmospheric chemistry, no shallow coastal environments for early organisms to colonize, no mountain building to drive tectonic processes. The birth of cratons during the Archean was, in a very real sense, the birth of Earth as we know it. The Archean Earth was a planet of fire. Volcanic activity during this eon was far more intense, far more frequent, and far more diverse than anything seen in recent geological history. This volcanism was not merely a surface phenomenon, but a manifestation of Earth's internal heat, still vastly greater than today, seeking ways to escape to the surface. Understanding Archean volcanism is crucial to understanding the entire eon, for it was volcanism that built much of the early crust, shaped the early atmosphere, and possibly even influenced the origin and early evolution of life. The most distinctive volcanic rock of the Archean is komatite, a rock type so rare in younger geological periods that when it does occur, it is considered highly anomalous. Komatite is an ultramafic volcanic rock, meaning it is exceptionally rich in magnesium and iron, and poor in silica compared to typical volcanic rocks like basalt. To form komatite, mantle rock must melt at temperatures exceeding 1600 degrees Celsius and possibly reaching as high as 1700 degrees or more. These temperatures are at least 250 degrees hotter than typical modern volcanic temperatures and require a mantle that is significantly hotter than today's. The very existence of komatite in Archean rocks tells us something profound about early Earth. The planet's interior contained more heat. This heat could generate higher temperatures in the mantle, and these higher temperatures could produce melts that would erupt at the surface as komatite lavas. These eruptions would have been spectacular, with lava flows that were extremely fluid, capable of traveling great distances before solidifying. Some Archean komatite flows are over 100 kilometers long, testament to the extraordinary fluidity of these ultra-hot lavas. Komatite flows have a distinctive texture called spinifex texture, named after an Australian grass with a similar spiky appearance. This texture consists of large blade-like crystals of olivine that grew rapidly as the lava cooled, producing a rock that under the microscope looks like a crystalline forest frozen in stone. The formation of spinifex texture requires rapid cooling of very hot lava, conditions that were apparently common in the Archean, but are essentially unknown in modern volcanism. As the Archean progressed, komatite became less common. In the Eoarchean and Paleoarchean, komatites were relatively abundant in many greenstone belts. By the Mesoarchean, they were becoming less frequent. In the Neoarchean, true komatites were rare, though some related ultramafic volcanic rocks still occurred. This decline reflects the gradual cooling of Earth's mantle over time. As the mantle cooled, it became increasingly difficult to generate the extreme temperatures needed for komatite formation. Today, komatites are essentially absent from the volcanic record, with only a handful of possible examples in the entire Phanerozoic. But komatite was not the only type of Archean volcanism. Basalts, the most common volcanic rock type today, were also abundant in the Archean. These mafic volcanic rocks erupted at temperatures around 1200 to 1300 degrees Celsius, formed in various settings. Some were oceanic basalts, similar to modern mid-ocean ridge basalts, produced by seafloor spreading if anything resembling modern plate tectonics was operating. Others were produced in volcanic arc settings if subduction was occurring. Still others may have been produced by mantle plumes or other processes unique to the hotter early Earth. More evolved volcanic rocks, richer in silica and more similar to modern andesites and rhyolites, also occur in the Archean record, particularly in the Neo-Archean. These rocks suggest that by late in the Eon, processes of magmatic differentiation and crustal remelting were producing the full spectrum of volcanic rock compositions we see today. The presence of these more silica-rich volcanic rocks is often taken as evidence for the operation of processes similar to modern subduction, where oceanic crust is recycled into the mantle, melted and erupted at volcanic arcs. The eruption style of Archean volcanoes is another area of intense interest. Some eruptions were effusive, producing lava flows that spread across the surface. This was likely the dominant style for komatiite and many basalts, but explosive eruptions also occurred, particularly for more silica-rich magmas. The evidence comes from volcanic ash deposits, now metamorphosed into rocks, that are interbedded with lava flows and sedimentary rocks in greenstone belts. These ash layers, some of which can be traced for tens of kilometers, indicate volcanic explosions powerful enough to loft material high into the atmosphere. Submarine volcanism, eruptions occurring underwater on the ocean floor, was probably even more common than subaerial volcanism during much of the Archean, simply because most of the planet's surface was covered by ocean. Submarine volcanic eruptions behave differently from terrestrial ones. The water quenches the lava rapidly, often producing a distinctive texture called pillow lava, where the molten rock forms bulbous, pillow-shaped masses as its surface solidifies in contact with cold water. Pillow lavas are common in Archean greenstone belts, providing clear evidence of underwater eruption. The gases released during Archean volcanic eruptions were crucial in shaping the early atmosphere. Volcanoes exhale a mixture of gases, including water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, nitrogen, and various other compounds. In the early Archean, volcanic outgassing was one of the primary sources of atmospheric gases, gradually building up the envelope of air that surrounds the planet. The high levels of volcanism meant that gas input to the atmosphere was much greater than today, though the exact composition of this volcanic gas is still debated. One particularly important aspect of Archean volcanism was its relationship to metallic ore formation. Many of the world's most valuable ore deposits are found in Archean rocks, particularly in greenstone belts. Gold deposits, including some of the richest gold mines on Earth, are associated with Archean volcanic and metamorphic rocks. The gold was concentrated by hydrothermal fluids, hot water rich in dissolved metals, that circulated through the crust during and after volcanic activity. These fluids would precipitate gold and other metals when they encountered certain chemical or temperature conditions, creating ore bodies that humans would discover and mine billions of years later. Nickel sulfide deposits associated with komatiite intrusions are another important Archean resource. When komatiite magma was intruded into the crust rather than erupted at the surface, it could dissolve sulfur from the surrounding rocks. As the magma cooled and crystallized, the sulfur would concentrate into a sulfide liquid that also concentrated nickel, copper, and platinum group elements. These deposits, found in places like the Kambalda region of Western Australia and Raglan in Canada, are major sources of these metals. Beyond precious and base metal deposits, Archean volcanism also led to the formation of massive volcanic-hosted massive sulfide deposits, where hot hydrothermal fluids venting on the seafloor precipitated metal sulfides. These deposits contain copper, zinc, lead, and other metals, and are important ore resources. The intense volcanic and hydrothermal activity of the Archean created ideal conditions for forming such deposits, leaving a legacy of mineral wealth that continues to be exploited today. The physical landscape created by Archean volcanism would have been dramatic. Imagine standing on the shore of that ancient ocean and looking inland. The land would be dominated by volcanic features, shield volcanoes, perhaps similar to those in Hawaii, but even larger, built up by countless lava flows over millions of years. Stratovolcanoes, steep-sided cones built up by alternating lava flows and explosive eruptions, would punctuate the horizon. Vast fields of volcanic rock, some still glowing with heat, would stretch to the horizon. And everywhere, steam and volcanic gases would rise from vents and fumaroles, their sulfurous smell carrying on the wind. The volcanic rocks themselves, once formed and cooled, would undergo transformation. In the hot, geologically active Archean Earth, rocks were quickly buried and subjected to high temperatures and pressures. This metamorphism converted original volcanic rocks into new rock types. Basalts became greenschist or amphibolite, taking on a greenish color from metamorphic minerals like chlorite and actinolite. This is where the term greenstone belt comes from. The metamorphosed volcanic rocks have a characteristic green hue. Komatiites also metamorphosed, often forming serpentinite, a slippery greenish rock that forms when ultramafic rocks react with water at elevated temperatures. Intrusive igneous rocks, magmas that cooled and solidified beneath the surface rather than erupting, were also common in the Archean. Great volumes of granite intruded into older rocks, forming plutons that ranged from a few kilometers to hundreds of kilometers across. These granites often showed evidence of multiple stages of intrusion, with older granite being intruded by younger granite in a complex history that could span tens of millions of years. The formation of these granites was part of the process of continental differentiation, extracting silica-rich, buoyant material and concentrating it in the growing cratons. Layered igneous intrusions represent another important Archean rock type. These are large bodies of mafic to ultramafic magma that cooled slowly, allowing minerals to crystallize and settle in layers based on their density. The result is a rock body with distinct layers of different mineral compositions, sometimes hundreds of meters thick. Some of these layered intrusions contain concentrations of valuable metals like chromium and platinum group elements, making them important economic resources. As we survey the full range of Archean volcanic and igneous rocks, we see a planet in geological overdrive, processing vast volumes of material from the mantle, building crust, releasing gases, and creating the raw materials from which continents would be constructed. This was not a quiet Earth slowly evolving, but a dynamic, violent, spectacular world, where fire and stone engaged in an endless dance of creation and destruction. Understanding this volcanism helps us appreciate the extraordinary nature of the Archean and the vast difference between early Earth and the more sedate planet we inhabit today. Perhaps no aspect of the Archean Earth would seem more alien to modern humans than its atmosphere. Step back in time to that ancient world, and you would immediately face a critical problem. You could not breathe. Not because the air is too thin or too thick, but because it lacks the one gas that is, to us and most complex organisms, absolutely essential: free molecular oxygen. The Archean atmosphere was, for most of its duration, essentially devoid of the oxygen that makes up 21% of today's air. This single difference had cascading effects on every aspect of the planet's chemistry, climate, and biology. The atmospheric composition of the early Archean is reconstructed through multiple lines of evidence. The study of ancient rocks and minerals that preserve information about atmospheric chemistry, theoretical models of atmospheric evolution, and comparisons with the atmospheres of other planets. While the exact percentages are debated, the overall picture is fairly clear. The Archean atmosphere was dominated by nitrogen, just as today, though possibly in slightly different proportions. Carbon dioxide was present at much higher levels than today, perhaps 100 to 1,000 times the modern pre-industrial concentration of 280 parts per million. Methane, a powerful greenhouse gas produced by early life forms, may have been present at levels of 100 to 1,000 parts per million, or even higher, compared to modern pre-industrial levels of about 700 parts per billion. Water vapor would have been abundant, especially over the warm Archean oceans, contributing to the greenhouse effect. Various sulfur-containing gases, including hydrogen sulfide and sulfur dioxide, would have been present from volcanic emissions. Trace amounts of other gases like carbon monoxide, hydrogen, and ammonia might also have been present, though their concentrations and roles remain areas of active research. What was conspicuously absent, or nearly so, was free oxygen. Estimates suggest oxygen levels were less than 1,000% of modern levels, and possibly as low as 100,000%. This absence of oxygen is confirmed by several types of geological evidence. One of the most compelling comes from the study of sulfur isotopes in ancient rocks. Sulfur has 4 stable isotopes: sulfur-32, sulfur-33, sulfur-34, and sulfur-36. In modern Earth, these isotopes are distributed in a predictable pattern, but in rocks older than 2,450 million years ago, we find something unexpected: mass-independent fractionation of sulfur isotopes. This means the isotopes are distributed in ways that cannot be explained by normal chemical or biological processes, but can be explained by ultraviolet light directly breaking down sulfur dioxide in the upper atmosphere. This process of photolysis by ultraviolet light can only occur if there is no ozone layer to absorb the UV radiation before it reaches sulfur-bearing gases, and an ozone layer can only exist if there is free oxygen in the atmosphere to form ozone. The presence of mass-independent sulfur fractionation in Archean rocks thus proves that free oxygen was essentially absent. The disappearance of this signal around 2,400,000,000 to 2,350,000,000 years ago marks the Great Oxygenation Event, when oxygen levels rose enough to form an ozone layer and shield sulfur dioxide from UV photolysis. Another line of evidence comes from the presence of certain minerals in ancient riverbeds and beach deposits. Minerals like uraninite and pyrite are unstable in the presence of oxygen. They react and break down. Yet in Archean sedimentary deposits, we find these minerals as detrital grains, meaning they were weathered from rocks, transported by rivers, and deposited in sediments while remaining intact. This is only possible if the atmosphere and river water lacked free oxygen. The presence of these minerals in rocks older than 2,300,000,000 years ago, but their absence in younger deposits provides additional confirmation of the timing of atmospheric oxygenation. The lack of oxygen had profound effects on Archean climate. Oxygen is a relatively inert gas that does not contribute much to the greenhouse effect. The gases that did dominate the Archean atmosphere, particularly carbon dioxide and methane, are powerful greenhouse gases. As mentioned earlier, this intense greenhouse effect was necessary to keep the planet from freezing despite the fainter young sun. Computer models suggest that without multiple percent carbon dioxide in the atmosphere, along with potentially significant methane, Earth's average temperature would have been below freezing, contradicting the geological evidence for liquid water. Methane deserves special attention because it may have played a particularly important role in Archean climate. Methane is about 30 times more effective than carbon dioxide at trapping heat over a century timescale. Even modest concentrations could produce significant warming, but methane has a relatively short lifetime in an oxygen-rich atmosphere, about a decade, because it reacts with oxygen and hydroxyl radicals. In the Archean atmosphere lacking oxygen, methane would have had a much longer lifetime, potentially lasting hundreds or thousands of years before being destroyed by other processes like ultraviolet photolysis. This means methane could accumulate to much higher levels than possible today. Some researchers have proposed that high methane concentrations during the Archean might have produced a hydrocarbon haze, similar to the haze we observe in the atmosphere of Saturn's moon Titan. On Titan, methane in the upper atmosphere is broken apart by ultraviolet light, and the resulting fragments recombine into complex organic molecules that form tiny particles. These particles scatter light, creating a thick orange-brown haze that envelops the moon. Something similar might have occurred on Archean Earth, creating what planetary scientists call an orange Archean. This hypothetical hydrocarbon haze would have had complex effects on climate. On one hand, the haze particles would absorb sunlight in the upper atmosphere, warming that region while cooling the surface, a so-called anti-greenhouse effect. On the other hand, the haze would also trap infrared radiation, contributing to warming. The net effect would depend on the size and composition of the haze particles, the thickness of the haze layer, and the concentrations of other atmospheric gases. Some models suggest the haze could have helped stabilize Archean climate by providing a kind of thermostat, thickening when methane production increased and thinning when it decreased. The appearance of the Archean sky would have been dramatically different from today's blue expanse. The blue color of modern sky comes from Rayleigh scattering, the same process that makes sunsets red, but the exact color depends on the composition of the atmosphere and the wavelength of sunlight. With high carbon dioxide and possible methane haze, the Archean sky might have appeared orange, pink, or reddish rather than blue. During sunrise and sunset, the colors would have been even more dramatic, with the low-angle sunlight passing through more atmosphere and producing spectacular displays of color that we can scarcely imagine. The absence of an ozone layer meant that ultraviolet radiation from the sun reached the surface largely unfiltered. For modern organisms, including humans, this would be instantly lethal. UV radiation damages DNA and proteins, causing mutations and cell death. In the Archean, this posed a significant challenge for early life. Organisms living at the surface or in shallow water would be constantly bombarded by UV radiation. This may explain why the earliest life seems to have been concentrated in deeper water environments, or in locations like hot springs where dissolved minerals in the water could provide some UV shielding, or in other protected niches. However, UV radiation was not entirely harmful. In fact, it may have played a crucial role in the origin of life. UV photons have enough energy to drive chemical reactions that would not occur otherwise, potentially helping to synthesize complex organic molecules from simpler precursors. Laboratory experiments have shown that UV irradiation of simple gas mixtures can produce amino acids, sugars, and even nucleobases, the building blocks of RNA and DNA. So while UV was a hazard for established organisms, It may have been an asset during the chemical evolution that led to life's origin. The atmospheric pressure during the Archean is another area of uncertainty. Some models suggest it may have been higher than today, perhaps 2 to 10 times modern pressure, though other estimates suggest pressures closer to today's values. Higher pressure would have several effects. It would shift the boiling point of water higher, allowing liquid water to exist at higher temperatures. It would affect the solubility of gases in seawater, and it would influence climate by changing how greenhouse gases absorb and emit radiation. As the Archean progressed, the atmosphere underwent gradual changes. The most significant of these changes were related to biology. Once life appeared and began to influence atmospheric chemistry, a new factor entered the equation: metabolically produced gases. Early organisms, using various types of metabolism adapted to the anoxic Archean environment, would have released methane, hydrogen, and possibly other gases. Later, the evolution of photosynthesis would begin producing oxygen, though in quantities too small to accumulate initially. There is evidence for transient increases in oxygen levels during the Archean, sometimes called whiffs of oxygen. These are brief periods, lasting perhaps a few million years, when oxygen concentrations rose above the background level before declining again. Geochemical signatures in rocks around 2,980,000,000, 2,700,000,000, and 2,500,000,000 years ago suggest such whiffs occurred. These may represent times when photosynthetic organisms were particularly productive, or when geological conditions allowed oxygen to accumulate temporarily, before being consumed by reactions with reduced gases and minerals. Despite these whiffs, the overall picture is clear. For most of its duration, the Archean atmosphere was fundamentally reducing rather than oxidizing. It was an atmosphere in which iron, sulfur, and organic compounds existed in reduced rather than oxidized states. It was an atmosphere that could not support complex life as we know it, but that was perfectly suited to the anaerobic microorganisms that dominated the Archean biosphere. Understanding this alien atmosphere is crucial to understanding how the planet evolved and how life adapted to the challenging conditions of early Earth. The question of when and how life originated on Earth is one of the most profound mysteries in science, and the Archean Eon is at the heart of this mystery. While life may have originated in the late Hadean, the oldest definitive evidence for life comes from the Archean, and it was during this eon that life transitioned from whatever simple chemical systems first deserved the name alive to the diverse microbial ecosystems that would set the stage for all subsequent evolution. The very definition of life is debated, but most scientists agree on certain key characteristics: the ability to reproduce, to evolve through natural selection, to maintain internal organization distinct from the environment, and to carry out metabolism using energy to build complex molecules from simpler ones. The origin of life was the emergence of a chemical system with these properties. How this happened remains unclear, but the Archean geological record preserves clues. The earliest evidence for life on Earth comes from rocks in western Greenland, dating to approximately 3,700,000,000 years ago. These rocks contain graphite, the mineral form of carbon, with an isotopic composition suggesting a biological origin. Carbon has two stable isotopes, carbon-12 and carbon-13. Biological processes, particularly photosynthesis, preferentially use the lighter carbon-12, leaving organic matter enriched in this isotope compared to inorganic carbon. The graphite in these ancient rocks shows just such an enrichment, suggesting it formed from biological material. Even older potential evidence exists, though it is more controversial. In Quebec, Canada, microscopic filaments in rocks associated with hydrothermal vents have been dated to between 3 billion, 800 million, and 4 billion, 300 million years ago. These filaments, if genuinely biological, would be the oldest known fossils. However, some researchers question whether they are truly biological or whether they might be artifacts of geological processes. The debate continues, illustrating how difficult it is to identify ancient life when the evidence has been transformed by billions of years of heat, pressure, and chemical alteration. More definitive fossil evidence appears around 3 billion, 500 million years ago with the appearance of stromatolites, which we will discuss in detail shortly. These layered structures, formed by microbial mats, provide clear evidence that by the mid-Archean, life had not only appeared, but had become abundant enough to create visible structures in the rock record. The microorganisms that built these stromatolites were almost certainly prokaryotes, simple single-celled organisms lacking a nucleus or other membrane-bound organelles. Two major domains of life are represented in the Archean: bacteria and archaea. These are fundamentally different groups of prokaryotes, as different from each other as either is from eukaryotes, the domain that includes all organisms with complex cells like plants, animals, and fungi. Both bacteria and archaea were present in the Archean, and both diversified into numerous forms, adapted to different environments and utilizing different types of metabolism. The earliest organisms were almost certainly anaerobic, meaning they did not use oxygen in their metabolism. This makes sense given the absence of oxygen in the Archean atmosphere and oceans. These early anaerobes would have obtained energy through various chemical reactions. Some may have been heterotrophs, consuming organic molecules produced by abiotic chemistry for energy. Others may have been lithotrophs, using inorganic chemical reactions to obtain energy, such as the reaction between hydrogen and carbon dioxide, or between iron and sulfur compounds. One particularly important group of early organisms were the methanogens, archaea, that produce methane as a byproduct of their metabolism. Methanogens thrive in anoxic environments rich in hydrogen and carbon dioxide, using hydrogen to reduce carbon dioxide into methane and obtaining energy in the process. These organisms may have been among Earth's earliest inhabitants, and they would have had a profound impact on atmospheric chemistry by continuously pumping methane into the atmosphere. The evolution of photosynthesis was perhaps the most important biological innovation of the Archean. Photosynthesis is the process of using light energy to build organic molecules, typically by fixing carbon dioxide into sugars. The earliest forms of photosynthesis were anoxygenic, meaning they did not produce oxygen as a byproduct. Anoxygenic photosynthesis uses compounds like hydrogen sulfide or ferrous iron as electron donors instead of water, releasing sulfur, sulfate, or ferric iron instead of oxygen. Several groups of bacteria can perform anoxygenic photosynthesis today, including purple sulfur bacteria and green sulfur bacteria. These organisms may represent descendants of the earliest photosynthetic lineages. In the Archean, before oxygen accumulated, anoxygenic photosynthesis may have been widespread, particularly in shallow water environments where light penetrated, and electron donors like hydrogen sulfide or ferrous iron were available from volcanic activity or weathering. The evolution of oxygenic photosynthesis, which uses water as an electron donor and produces oxygen, was a game changer. This process, performed today by cyanobacteria, algae, and plants, requires two photosystems working together to extract electrons from water, a challenging chemical feat. The evolution of oxygenic photosynthesis sometime in the Archean, possibly in the Meso-Archean or Neo-Archean, would eventually transform Earth's atmosphere and oceans, though the accumulation of oxygen would not become significant until after the end of the Archean. Evidence for when oxygenic photosynthesis evolved is hotly debated. Some researchers argue it appeared as early as 3,700 million years ago, based on stromatolite structures that resemble those formed by modern cyanobacteria. Others contend that cyanobacteria and oxygenic photosynthesis did not appear until much later, perhaps around 2,700 million years ago, or even at the very end of the Archean. Chemical biomarkers, molecular fossils that are the breakdown products of specific biological molecules, suggest cyanobacteria were present by at least 2,700 million years ago, but the evidence for earlier presence remains uncertain. What is clear is that once oxygenic photosynthesis evolved, it provided a tremendous advantage. Water is much more abundant than hydrogen sulfide or ferrous iron, meaning photosynthetic organisms could colonize a wider range of environments. The oxygen produced, while initially consumed by reactions with iron and other reduced substances, would eventually begin to accumulate, setting the stage for the Great Oxygenation Event. Early Archean life would have been restricted to certain environments. The intense ultraviolet radiation at the surface, discussed earlier, would have made shallow water and land surfaces hazardous. Deep-sea hydrothermal vents, where hot mineral-rich water erupts from the seafloor, may have been important refuges. These environments, shielded from UV by kilometers of water, provided chemical energy from the reactions between hot vent fluids and cold seawater. Modern hydrothermal vent communities, teeming with life supported by chemosynthesis rather than photosynthesis, may give us a glimpse of what early Archean vent communities were like. Shallow water environments, particularly those with some UV protection, such as locations under microbial mats or in waters clouded by dissolved iron or other minerals, would have been important for photosynthetic organisms. Coastal hot springs, similar to those in modern Yellowstone National Park, may also have been significant habitats. The varying temperature and chemistry in these environments create diverse microhabitats, and some researchers have proposed that the origin of life itself might have occurred in such settings. The diversity of Archean life would have been impressive at the microscopic level, even though all known Archean organisms were single-celled prokaryotes. Different species would have been adapted to different temperatures, different chemical conditions, different light levels, and different sources of energy and nutrients. Some would have been specialists, thriving only in narrow ranges of conditions. Others would have been generalists, capable of surviving in diverse environments. Competition, cooperation, and evolution would have been operating, shaping the ecosystem just as they do today. Fossilized microorganisms from the Archean, while rare, have been found in some exceptionally preserved rocks. These microfossils include spherical and filamentous forms, some only a few micrometers in size. Under the electron microscope, these ancient cells sometimes show features like cell walls and evidence of cell division. While any individual microfossil might be ambiguous, the collective evidence from multiple sites and ages builds a convincing case for abundant and diverse microbial life throughout the Archean. Genetic analysis of modern organisms also provides insights into Archean life. By comparing the genomes of diverse modern organisms, scientists can infer what genes and metabolic pathways their common ancestors must have possessed. These analyses suggest that the last universal common ancestor, or LUCA, the organism from which all modern life descended, lived sometime in the Archean, or possibly late Hadean. LUCA was probably a thermophilic organism, meaning it thrived at high temperatures, and it possessed genes for a surprising variety of metabolic pathways, suggesting it lived in a chemically complex environment, possibly near hydrothermal vents. As the Archean progressed, life became more abundant and more diverse. Microbial mats layered communities of different microorganisms living together became common in shallow water environments. These mats would have been slimy, smelly places where different organisms cooperated and competed in complex food webs. Photosynthetic organisms on the surface would capture light energy and fix carbon dioxide. Beneath them, other organisms would feed on the organic matter produced, releasing various waste products. Deeper still, different species would carry out different metabolic reactions, creating a stratified ecosystem where each layer had its own chemistry and community. The impact of life on the Archean environment cannot be overstated. Even simple anaerobic microbes, present in sufficient numbers, would have influenced ocean chemistry, removing some chemicals from solution and releasing others. The evolution of photosynthesis would have begun removing carbon dioxide from the atmosphere and releasing oxygen, even if oxygen initially was consumed by reactions with iron and other reduced substances. Methanogens would have been producing methane, affecting the greenhouse effect and thus climate. Life was not merely adapting to its environment, but actively changing that environment, setting up feedback loops that would become increasingly important as the eon progressed. Among the most striking and important fossils of the Archean are stromatolites, layered structures created by the growth and metabolic activity of microbial mats. These formations, which can range from centimeters to meters in height and can extend for kilometers, represent one of the clearest pieces of evidence for early life. They tell us not only that life existed, but that it was abundant enough and organized enough to create macroscopic structures visible to the naked eye. In studying stromatolites, we are looking at the work of countless generations of microorganisms, layer upon layer, accumulating over centuries or millennia. The word stromatolite comes from Greek roots meaning layered rock, an apt description of these structures. At their simplest level, stromatolites are sedimentary structures created when microbial mats trap and bind sediment particles, cementing them together through the action of sticky organic compounds secreted by the microorganisms. The microbes, which in modern examples are typically photosynthetic organisms like cyanobacteria, form a thin film on a surface. This film is coated with a mucilaginous layer that traps sand and silt particles settling from the water. The microorganisms then grow upward through the sediment, establishing a new layer on top of the old one. This process repeats day after day, year after year, creating the characteristic laminated structure. Whether Archean stromatolites were built by cyanobacteria or by other types of photosynthetic bacteria remains a subject of ongoing research. Archean stromatolites are found in numerous locations around the world, but some of the most famous and best preserved examples come from Western Australia. In the Pilbara region, stromatolites dating to 3,480,000,000 years ago have been found in the Dresser Formation. These structures, some of the oldest known stromatolites, appear as dome-shaped mounds and columnar structures in ancient chert deposits. Their age places them early in the Archean, showing that by the mid-Paleo-Archean, microbial mats were already building substantial structures. Even older potential stromatolites exist. In Greenland's Isua supracrustal belt, structures resembling stromatolites have been found in rocks dating to 3,700,000,000 years ago, or possibly older. However, these ancient structures have been subjected to such intense metamorphism that their biological origin remains debated. Some researchers argue they represent genuine stromatolites, making them the oldest evidence for life. Others contend they might be abiogenic structures created by non-biological geological processes. The debate illustrates the challenges of identifying ancient life when the rocks have been transformed by heat and pressure. The formation process of stromatolites is intimately connected to the daily and seasonal cycles of microbial growth. During daylight hours, photosynthetic microorganisms in the mat are active, producing oxygen or other metabolic products, and secreting the sticky compounds that trap sediment. At night, growth slows or stops. This daily cycle can sometimes be detected in the fine-scale structure of stromatolites as alternating light and dark bands called microbands. Some researchers have suggested these might represent true daily laminations, though this interpretation is controversial. On longer timescales, seasonal or other environmental variations can produce the more obvious banding seen in most stromatolites. During periods of high sediment input, perhaps during storms or seasonal flooding events, thicker layers of sediment might be trapped. During calmer periods, less sediment accumulates, and the microbial mat might be more dominant in the layer. The result is alternating bands of sediment-rich and organic-rich material, creating the distinctive layered appearance. The shape of stromatolites varies widely. Some are flat, essentially horizontal layers, with little relief, called stratiform stromatolites. Others form domes, rounded mounds that can be several meters across. Still others grow as columns, cylinders of layered rock rising vertically from the seafloor. Some stromatolites branch, with one column splitting into two or more. The morphology depends on various factors, including water depth, current strength, sediment type, and the specific microorganisms involved in building the structure. One particularly interesting type is conical stromatolites, structures that form steep-sided cones. Modern examples of conical stromatolites are rare, but can be found in a few locations like Lake Thetis in Western Australia. Studies of these modern analogues suggest the conical shape might be related to the behavior of photosynthetic microorganisms, particularly their tendency to move toward light. As a cone grows upward, organisms at the tip receive the most light and grow fastest, maintaining the pointed shape. This phototaxis, the movement toward light, combined with other factors, produces the distinctive conical morphology that is also seen in some ancient Archean examples. Not all Archean stromatolites contain well-preserved microfossils of the organisms that built them. In fact, most do not. The spongiostromate texture, where no cellular remains are visible, is most common. This might seem puzzling. How can we be sure these structures are biological if we cannot see the organisms? The answer lies in several lines of evidence. First, the structures themselves are too regular and too similar to modern biologically formed structures to be easily explained by purely abiogenic processes. Second, the presence of organic carbon with isotopic signatures indicating biological activity provides chemical evidence. Third, in some exceptionally preserved examples, actual microfossils are present, confirming the biological origin. In the rare cases where microfossils are preserved, they provide a window into the organisms that built Archean stromatolites. These fossils include spherical cells, filamentous chains of cells, and various other morphologies. Under high-powered microscopes, particularly electron microscopes, these ancient cells sometimes show remarkable detail, including cell walls, internal structures, and even evidence of cell division. While identifying the exact species is usually impossible, and determining whether these were true cyanobacteria or other types of prokaryotes remains controversial, the general character of these fossils indicates they were photosynthetic microorganisms adapted to shallow water environments. The abundance of stromatolites changed dramatically over geological time. They first appear around 3,500 million years ago in the Archean, become common later in the Archean. and reached their peak abundance in the Proterozoic Eon between 2,500,000,000 and 500,000,000 years ago. During the late Proterozoic, stromatolites were extremely abundant, forming extensive reefs in shallow marine environments around the world. However, their abundance declined sharply at the beginning of the Cambrian period, about 540 million years ago, and they are relatively rare today. This decline is usually attributed to the evolution of grazing organisms, particularly animals with hard shells that could scrape microbial mats off surfaces and consume them. This phenomenon, called the Cambrian substrate revolution, fundamentally changed marine ecosystems. Suddenly, microbial mats were under constant attack from grazers, and they could only survive in environments where grazers were absent or rare. This explains why modern stromatolites are found primarily in extreme environments like the hypersaline waters of Shark Bay, Australia, or the alkaline hot springs of Yellowstone, places where few animals can survive. Shark Bay, on the western coast of Australia, hosts the most extensive modern stromatolite formations. In certain shallow, hypersaline areas of the bay, stromatolites grow abundantly, creating structures remarkably similar to those found in the fossil record. These modern stromatolites are built primarily by cyanobacteria and provide invaluable opportunities to study the processes of stromatolite formation in real time. Researchers can observe how the microbial mats respond to environmental changes, how sediment is trapped, how the structures grow, and what controls their morphology. The study of modern stromatolites has also revealed that their formation is more complex than once thought. The microorganisms involved form diverse communities, with multiple species interacting in intricate ways. Different layers within the mat can have different communities, adapted to different levels of oxygen, different light intensities, and different chemical conditions. Some organisms are photosynthetic, producing oxygen. Others are anaerobic, thriving in the oxygen-free depths of the mat. Still others are mobile, moving up and down through the mat in response to daily cycles of light and chemistry. This complexity in modern stromatolites suggests that ancient Archean stromatolites might also have hosted diverse microbial communities, even though all the organisms involved would have been prokaryotes. Different species would have occupied different niches within the mat structure, creating a stratified ecosystem where cooperation and competition occurred simultaneously. The evolution of such complex microbial communities early in Earth's history demonstrates that even simple organisms can create sophisticated ecological structures. The geochemical signatures preserved in stromatolites provide additional information about ancient environments. The types of minerals precipitated, the isotopic ratios of carbon and sulfur, the presence or absence of certain trace elements, all can inform us about the chemistry of the water in which the stromatolites grew. For instance, carbon isotope ratios can indicate how much photosynthesis was occurring and whether it was oxygenic or anoxygenic. Sulfur isotope patterns can tell us about sulfur cycling and the presence or absence of oxygen. Rare earth element patterns can indicate whether the water was influenced by hydrothermal activity or by continental weathering. In some Archean stromatolites, particularly those associated with banded iron formations, there is evidence for interaction between microbial activity and iron chemistry. The oxidation of dissolved ferrous iron by oxygen, produced through photosynthesis or potentially by an oxygenic iron-oxidizing photosynthesis, would cause iron to precipitate as ferric oxides. This creates alternating layers of iron-rich and iron-poor material within the stromatolite, visible as red and white or grey bands. These iron-bearing stromatolites provide some of the clearest evidence for the role of biology in altering ocean chemistry during the Archean. Stromatolites thus serve multiple roles in our understanding of the Archean. They are fossils, providing evidence that life existed and was abundant. They are ecosystems, hosting diverse communities of microorganisms. They are chemical factories, influencing the composition of seawater through their metabolic activities. And they are archives, preserving in their layers information about ancient environmental conditions that we can decode billions of years later. In studying stromatolites, we are reading a story written in stone by countless generations of microorganisms. A story that tells us about the dawn of life on our planet. Few rock types are as distinctive, as economically important, or as scientifically significant as banded iron formations. These striking rocks, with their alternating layers of iron-rich and iron-poor minerals, creating a banded appearance in shades of red, grey, and black, are essentially absent from the modern geological record, but were abundantly formed during the Archean and early Proterozoic. They represent a unique window into a time when Earth's oceans had a fundamentally different chemistry, when oxygen was beginning to accumulate, and when life was starting to exert a global influence on the planet's environment. A banded iron formation, usually abbreviated as BIF, is defined as a sedimentary rock consisting of alternating layers of iron-rich minerals and iron-poor minerals, typically chert. The iron-rich layers contain minerals like magnetite, hematite, siderite, and various iron silicates. The iron-poor layers consist mainly of chert, which is microcrystalline quartz, sometimes with minor amounts of other minerals. These layers can be as thin as millimeters or as thick as centimeters, repeating hundreds or thousands of times in a single formation. Some BIF units are hundreds of meters thick and extend laterally for hundreds of kilometers, representing vast quantities of precipitated iron. The oldest known banded iron formations date to the early Archean, around 3,800 million years ago, though they were relatively rare at this time. BIFs became much more common in the late Archean, from about 3 billion to 2,500 million years ago, and continued to form prolifically in the early Proterozoic until about 1,850 million years ago. After that, they essentially disappeared from the geological record, with only brief reappearances during certain unusual periods like the Neoproterozoic glaciations around 700 million years ago. This distinctive temporal distribution is one of the most intriguing aspects of BIFs. Why did they form abundantly for over 1 billion years and then stop? The answer lies in the changing chemistry of Earth's oceans and atmosphere, particularly with respect to oxygen. BIFs can only form under specific conditions. There must be abundant dissolved iron in the water. This iron must be oxidized to precipitate out of solution. And there must be relatively little sulfur in the system, because sulfur reacts with iron to form iron sulfide, which would prevent BIF formation. In the Archean Ocean, with its lack of dissolved oxygen, iron existed primarily as ferrous iron, which is soluble in water. This iron came from two main sources: submarine hydrothermal vents, where hot water leaching iron from oceanic crust erupted onto the seafloor, and weathering of continental rocks, which released iron that was transported by rivers to the ocean. The older Archean-type BIFs, called Algoma-type BIFs, were typically associated with volcanic rocks in greenstone belts and probably formed primarily from hydrothermal iron sources. Later BIFs, called Lake Superior type, after the famous deposits in the Great Lakes region, formed on continental margins and drew more of their iron from continental weathering. But having dissolved iron is not enough to form a BIF. Something must cause that iron to precipitate out of the water. This is where the story becomes complex and fascinating. Several mechanisms have been proposed for iron precipitation in BIFs. One widely discussed hypothesis involves the production of oxygen by photosynthetic organisms. If oxygen-producing cyanobacteria were present and photosynthesizing in shallow water, they would have produced oxygen that reacted immediately with dissolved ferrous iron, oxidizing it to ferric iron, which is insoluble and precipitates as iron oxide minerals like hematite or magnetite. This process creates an elegant connection between biology and geology. The oxygen produced by early life did not initially accumulate in the atmosphere because it was consumed as fast as it was produced by reactions with reduced substances, particularly the abundant dissolved iron in the oceans. Only after most of the iron had precipitated out, after billions of tons of iron oxides had accumulated on the seafloor as BIFs, could oxygen begin to accumulate in the atmosphere. BIFs thus represent a kind of oxygen buffer, documenting a time when oxygen was being produced but was not yet free to accumulate. However, the story may be more complex. Recent research has shown that BIFs can also form through anoxygenic iron-oxidizing photosynthesis, a process where certain bacteria use ferrous iron directly as an electron donor for photosynthesis instead of water, producing ferric iron as a byproduct instead of oxygen. These photoferrotrophs, as they are called, can cause iron precipitation without producing any oxygen. In the Archean, before oxygen-producing cyanobacteria became dominant, photoferrotrophs may have been responsible for much BIF deposition. There is also evidence that purely abiotic processes could contribute to iron oxidation and BIF formation. Ferrous hydroxide, which forms when dissolved ferrous iron encounters alkaline conditions, is unstable and can spontaneously decompose to produce metallic iron and release hydrogen gas. The metallic iron then reacts with water to produce ferric iron. This process, discovered through laboratory experiments on Archean ocean analogues, suggests that iron could have been oxidized and precipitated even in the complete absence of life. The reality is probably that all these mechanisms played roles at different times and places. Early Archean BIFs might have formed through primarily abiotic processes or through anoxygenic photosynthesis. Later, Archean and early Proterozoic BIFs increasingly involved oxygen-producing photosynthesis as cyanobacteria became more abundant. The disappearance of BIFs around 1,850 million years ago occurred when the ocean became fully oxygenated, so that iron was oxidized and precipitated long before reaching the open ocean where BIFs formed. The banding in BIFs, the alternation between iron-rich and iron-poor layers, has been explained in various ways. Some researchers suggest the bands represent annual varves, with each band representing 1 year of deposition. In this interpretation, variations in the supply of iron or silica, perhaps linked to seasonal changes in weathering rates, river discharge, volcanic activity, or biological productivity, would create the observed banding. If true, this would mean a typical BIF with thousands of bands represents thousands of years of deposition. Other explanations invoke longer-term cycles. The bands might represent cycles of tens or hundreds of years, related to variations in ocean circulation, upwelling patterns, or climatic fluctuations. Or they might be related to biological cycles, with blooms of photosynthetic organisms producing pulses of oxygen that precipitate iron-rich layers, alternating with quieter periods when silica-rich chert accumulates. The question remains unresolved and may have different answers for different BIFs. The economic importance of BIFs cannot be overstated. These formations are the source of most of the world's iron ore. Deposits like those in the Hamersley Basin of Western Australia, the Superior Province of Canada, the Quadrilatero Ferrífero of Brazil, and the Transvaal Basin of South Africa have been mined for decades and supply much of the iron used in global steel production. The high-grade iron ore in these deposits, sometimes exceeding 60% iron content, formed when later weathering concentrated the iron by removing silica, leaving behind nearly pure iron oxide. The distribution of BIFs also provides information about ancient continental configurations. Because Lake Superior-type BIFs form on continental margins, mapping their locations can help reconstruct where continents were positioned in the Archean and early Proterozoic. The orientation and extent of BIF formations can indicate ancient coastlines, ocean basins, and tectonic boundaries, contributing to our understanding of how cratons assembled and how the continents evolved. Geochemical analysis of BIFs yields additional insights. Rare earth element patterns can distinguish between BIFs that formed primarily from hydrothermal sources versus those with significant continental input. Europium anomalies, where the concentration of the element europium deviates from expected levels, are particularly informative. Positive europium anomalies indicate hydrothermal influence, because europium behaves differently than other rare earth elements at the high temperatures of hydrothermal systems. Older Archean BIFs often show these positive europium anomalies, while younger BIFs do not, confirming a shift from hydrothermal to continental weathering sources over time. Iron isotope ratios in BIFs provide yet another line of evidence about formation processes. Different iron oxidation mechanisms produce different isotopic signatures. By measuring these ratios in BIFs of different ages, researchers can infer how iron oxidation processes changed over time, potentially distinguishing between abiotic oxidation, anoxygenic photosynthetic oxidation, and oxidation by free oxygen from oxygenic photosynthesis. The association between BIFs and stromatolites in some locations is particularly intriguing. In the Hamersley Basin of Western Australia, stromatolites are found interbedded with BIFs, providing strong evidence for biological involvement in BIF formation. The microorganisms building the stromatolites were likely producing oxygen that oxidized iron, directly linking biological and geological processes. These associated deposits provide some of the best evidence for early photosynthesis and its environmental impact. As we contemplate these banded rocks, alternating red and grey in striking patterns, we are looking at records of a planet in transition. BIFs document the gradual filling of the iron sink in the oceans, the removal of dissolved iron that had accumulated over billions of years in the anoxic Archean seas. They mark the slow progress toward an oxygenated world, a transition driven by the metabolic activity of countless microorganisms over vast spans of time. They are, in a very real sense, the tombstones of the Archean ocean chemistry, marking the death of one world and the birth of another. The evolution of photosynthesis stands as one of the most consequential biological innovations in Earth's history, ranking alongside the origin of life itself in its impact on the planet. While the exact timing remains debated, photosynthesis emerged sometime during the Archean Eon, perhaps as early as 3,700,000,000 years ago, or possibly later. This new metabolic capability allowed organisms to harness the energy of sunlight, the most abundant and reliable energy source available, transforming them from dependence on environmental chemistry to agents capable of fundamentally altering that chemistry. To appreciate the significance of photosynthesis, we must understand what came before. The earliest organisms on Earth were chemotrophs, obtaining energy from chemical reactions. Some were heterotrophs, consuming organic molecules that had accumulated through abiotic synthesis. Others were lithotrophs, deriving energy from inorganic reactions such as the oxidation of hydrogen or iron, or reduced sulfur compounds. While these metabolisms allowed life to persist, they were ultimately limited by the availability of suitable chemical substrates. Life was confined to specific environments where the right chemistry existed. Photosynthesis changed everything by making energy available anywhere sunlight could reach. Suddenly, organisms could colonize the vast shallow waters of the global ocean, no longer restricted to hydrothermal vents or other localized chemical environments. The evolutionary advantages were enormous, and photosynthetic organisms would come to dominate Earth's primary productivity, a pattern that continues today, where photosynthesis, both in the oceans and on land, accounts for the vast majority of new organic matter production. But not all photosynthesis is the same. The earliest forms were almost certainly anoxygenic, meaning they did not produce oxygen. Anoxygenic photosynthesis uses simpler electron donors than water, substances like hydrogen sulfide, hydrogen gas, or ferrous iron. Several groups of modern bacteria perform anoxygenic photosynthesis, including purple sulfur bacteria, green sulfur bacteria, purple non-sulfur bacteria, and heliobacteria. These organisms may represent living relics of the earliest photosynthetic lineages, though they have certainly evolved substantially since the Archean. Consider purple sulfur bacteria, which thrive in sulfide-rich environments today. These organisms use hydrogen sulfide as an electron donor, producing elemental sulfur or sulfate as a byproduct instead of oxygen. The process requires only one photosystem and is chemically simpler than oxygenic photosynthesis. In the Archean Ocean, with its abundant dissolved sulfur compounds from volcanic activity, anoxygenic sulfur-based photosynthesis would have found ideal conditions. Similarly, photoferrotrophs, bacteria that use ferrous iron as an electron donor in anoxygenic photosynthesis, would have thrived in the iron-rich Archean seas. As discussed in the section on banded iron formations, these organisms may have played a major role in precipitating iron and forming BIFs. They provide a neat solution to a puzzle. How could stromatolites and BIFs co-occur in the absence of oxygen? Photoferrotrophs could build stromatolite structures while simultaneously causing iron precipitation, all without producing oxygen. The evolution of oxygenic photosynthesis was a more challenging feat. This process uses water as an electron donor, splitting water molecules to extract electrons and protons while releasing oxygen as a waste product. Water is a very stable molecule, difficult to split, requiring the evolution of photosystem 2, a complex molecular machine capable of catalyzing water oxidation. This system had to work in conjunction with photosystem Y, which handles the subsequent electron transfer reactions. The combination of these two photosystems, working together in what scientists call the Z's scheme, makes oxygenic photosynthesis possible. The organism that first accomplished oxygenic photosynthesis was ancestral to modern cyanobacteria, sometimes called blue-green algae, though they are bacteria, not algae. Cyanobacteria are the only prokaryotes capable of oxygenic photosynthesis, and all the oxygen in Earth's atmosphere, past and present, traces ultimately to these organisms or to eukaryotic organisms that acquired photosynthetic capability through the engulfment of cyanobacteria as endosymbionts. When did oxygenic photosynthesis evolve? This question remains one of the most contentious in studies of early life. Some lines of evidence suggest an early origin, perhaps as far back as 3,700,000,000 to 3,500,000,000 years ago. This evidence includes the morphology of certain ancient stromatolites, that resemble those formed by modern cyanobacteria, and carbon isotope patterns that some interpret as signatures of oxygenic photosynthesis. If true, this would place the origin of oxygenic photosynthesis early in the Archean. Other evidence suggests a later origin, perhaps around 2,700,000,000 years ago, or even at the very end of the Archean. This evidence includes the absence of unambiguous chemical biomarkers for cyanobacteria in rocks older than about 2,700,000,000 years, and the argument that the atmosphere and ocean remained essentially oxygen-free until near the end of the Archean, suggesting oxygenic photosynthesis was either absent or not. Very productive. Part of the difficulty in resolving this debate lies in distinguishing between the origin of oxygenic photosynthesis and its proliferation. Oxygenic photosynthesis might have evolved relatively early, but remained a minor metabolic process for hundreds of millions, or even 1,000,000,000 years before becoming dominant. During this long period, oxygen production might have been small enough that all the oxygen produced was consumed by reactions with reduced minerals and gases, leaving no oxygen to accumulate and no clear signature in the rock record. There is geochemical evidence for brief episodes of elevated oxygen, called whiffs of oxygen, at several points during the Archean. Samples from around 2,980,000,000, 2,700,000,000, and 2,500,000,000 years ago show signatures suggesting temporary increases in oxygen levels. These whiffs might represent periods when oxygenic photosynthesis was particularly productive, or when geological conditions allowed oxygen to accumulate temporarily before being consumed. They suggest that oxygenic photosynthesis existed and was producing oxygen, but that this oxygen was not yet accumulating permanently. The ecological impact of oxygenic photosynthesis in the Archean, even before oxygen accumulated significantly, would have been substantial. Organisms capable of using water as an electron donor had access to the most abundant substance on Earth's surface. They could colonize any environment where light penetrated, from shallow tide pools to the open ocean, no longer dependent on localized sources of hydrogen sulfide or ferrous iron. This competitive advantage would have allowed cyanobacteria to spread widely and gradually become the dominant primary producers. But there was a cost to this success. The oxygen produced by cyanobacteria was actually toxic to most other Archean organisms, which had evolved in an anoxic world and had no mechanisms to protect themselves from oxygen's damaging effects. Oxygen is a powerful oxidizing agent that can damage proteins, lipids, and DNA. For anaerobic organisms, oxygen exposure could be lethal. As cyanobacteria spread and oxygen production increased, they were essentially poisoning the environment for competitors. This gave cyanobacteria an additional advantage, reducing competition from anaerobic organisms. Over time, some organisms evolved tolerance to oxygen and eventually mechanisms to use oxygen in their metabolism. Aerobic respiration, the use of oxygen to oxidize organic matter and extract energy, is far more efficient than anaerobic metabolisms. An organism using aerobic respiration can extract about 18 times as much energy from a glucose molecule as one using fermentation. This efficiency gave aerobic organisms a tremendous competitive advantage once oxygen became available. The stage was set for an ecological revolution, though it would not be complete until well after the end of the Archean. The production of oxygen had cascading effects on biogeochemical cycles beyond just its direct impact on organisms. Oxygen reacts with methane, a greenhouse gas produced by methanogens. In an oxygenated atmosphere, methane has a short lifetime. In the anoxic Archean, methane could accumulate to high levels. As oxygen began to increase, even slightly, it would have begun destroying methane more quickly, potentially weakening the greenhouse effect. This could have contributed to cooling, and some researchers have linked the earliest glaciation events to temporary increases in oxygen that destroyed methane greenhouse warming. Oxygen also affects the cycling of numerous other elements. Sulfur chemistry changes dramatically in the presence of oxygen, as does the behavior of iron, manganese, and many other metals. The establishment of an oxidized surface environment meant that new minerals could form, minerals that require oxygen to precipitate. Some researchers have argued for a kind of mineral evolution, where the diversity of mineral types on Earth has increased over geological time as chemical conditions changed, with oxygenic photosynthesis being one of the major drivers of this diversification. The photosynthetic revolution also had implications for the carbon cycle. Photosynthesis removes carbon dioxide from the atmosphere and oceans, fixing it into organic matter. While much of this organic matter is recycled quickly through respiration or decomposition, some is buried in sediments, effectively removing carbon from the active carbon cycle for millions or billions of years. The burial of organic carbon in sediments is the ultimate source of oxygen accumulation in the atmosphere, because it represents reduced carbon that is not available to consume oxygen. As we look back on the Archean, the evolution and spread of photosynthesis, particularly oxygenic photosynthesis, emerges as the pivotal development that would transform Earth. While the Archean itself remained largely anoxic, with oxygen levels low or negligible for most of its duration, the stage was being set for change. The oxygen-producing organisms were evolving, spreading, diversifying, and gradually increasing their impact on global chemistry. The long Archean story of photosynthesis was building toward a climax that would come early in the subsequent Proterozoic Eon, the great oxygenation event when oxygen would finally accumulate in the atmosphere, transforming Earth irrevocably and opening new evolutionary possibilities. As the Archean drew to a close around 2,500 million years ago, Earth was a profoundly different planet than it had been at the Eon's beginning 1.5 billion years earlier. The Neo-Archean era, the final chapter of the Archean, from 2,800 million to 2,500 million years ago, witnessed dramatic developments that would set the stage for the great transformations of the subsequent Proterozoic Eon. The closing act of the Archean was not a quiet denouement, but a crescendo of geological and biological change. Perhaps the most significant development of the late Archean was the assembly of large continental masses, possibly including the first supercraton or small supercontinent. Throughout the Archean, cratons had been forming and growing, initially as isolated fragments scattered across a global ocean. By the Neo-Archean, these cratons were beginning to collide and amalgamate, driven by whatever tectonic processes were operating at the time. The collision of cratons produced distinctive geological features, including deformation zones, metamorphism, and the intrusion of granites. Around 2,700 million years ago, evidence suggests that several cratons may have assembled into a larger landmass that some geologists call Superior or Canorland. This proto-continent might have included parts of what are now North America, Greenland, parts of Northern Europe, and possibly fragments of other modern continents. The evidence for its existence comes from similarities in rock ages and types across these regions, paleomagnetic data suggesting these areas were once adjacent, and patterns of later rifting that seem to have broken this ancient landmass apart. If Superior existed, it represented a major milestone in Earth's evolution. For the first time, a substantial fraction of the planet's continental crust would have been gathered into a single large landmass, rather than scattered in small proto-continents. This assembly would have had implications for ocean circulation, climate, the weathering of continental rocks, and the supply of nutrients to the oceans. The formation of supercratons or supercontinents would become a recurring theme in Earth's subsequent history, with continents cycling between assembly and dispersal in a pattern that continues today. The late Archean also saw important changes in the style of continental crust formation. While earlier Archean cratons were dominated by TTG rocks formed through the partial melting of mafic crust, Neo-Archean cratons show abundant granite, particularly potassium-rich granite, formed through the remelting of earlier crust. These granites often formed in enormous volumes, creating vast plutonic complexes sometimes called granite blooms. The formation of these granites helped stabilize cratons by thickening the crust, concentrating radioactive heat-producing elements, and differentiating the crust chemically. Evidence for modern-style plate tectonics becomes increasingly clear in the Neo-Archean. Rock assemblages that closely resemble modern subduction zone sequences, including volcanic arcs, accretionary prisms, and ophiolites, appear in the rock record. This suggests that by late in the Archean, subduction of oceanic lithosphere beneath continents or other oceanic lithosphere was occurring in a manner similar to modern plate tectonics. Whether plate tectonics operated earlier in the Archean in a different form, or whether the Neo-Archean marks its initiation, remains debated, but by the end of the Eon, something recognizably similar to modern processes was underway. The late Archean atmosphere was beginning to show hints of the oxygen revolution to come. The whiffs of oxygen at 2,700,000,000 and 2,500,000,000 years ago suggested that oxygen production by photosynthetic organisms was increasing. While oxygen levels remained low, far below 1% of modern levels, the trend was clear. The long period of preparation, during which oxygen was produced but immediately consumed by reactions with reduced substances, was drawing to a close. The ocean's capacity to absorb oxygen through reactions with dissolved iron was becoming saturated as BIFs accumulated on the seafloor. Glaciation events occurred in the late Archean, providing evidence of climate variations. The oldest known glaciation in Earth's history occurred during the Meso-Archean around 2,900,000,000 years ago, based on the presence of glacial deposits in South Africa. Another glaciation may have occurred near the end of the Archean. These glaciations suggest that despite the greenhouse effect from carbon dioxide and methane, the planet was capable of cooling sufficiently to freeze water at high latitudes, or possibly even at lower latitudes, in what might have been an early snowball Earth event. The causes of these Archean glaciations are uncertain, but might relate to various factors. A temporary decline in methane levels, perhaps caused by a brief increase in oxygen that destroyed methane more rapidly than it could be produced, might have weakened the greenhouse effect and allowed cooling. Increased weathering of the newly assembled continental masses might have drawn down atmospheric carbon dioxide. Changes in Earth's orbit and axial tilt, which vary cyclically, might have altered the distribution of sunlight reaching the surface. Whatever the causes, these glaciations demonstrate that even in the Archean, Earth's climate system was capable of significant variations. Biological evolution continued throughout the late Archean. Cyanobacteria, the oxygen-producing photosynthesizers, were diversifying and spreading. Other bacterial lineages were exploring various metabolic strategies adapted to the changing chemical environment. Some evidence suggests that eukaryotes, organisms with complex cells containing a nucleus and other membrane-bound organelles, might have originated in the late Archean, though definitive fossils do not appear until the Proterozoic. The presence of steranes, chemical biomarkers derived from sterols that are produced primarily by eukaryotes, has been reported in rocks around 2,700,000,000 years old. Though this evidence remains contentious, if eukaryotes did originate in the late Archean, this would represent another major evolutionary innovation. Eukaryotes are fundamentally different from prokaryotes in their cellular organization, with their genetic material enclosed in a nucleus, with mitochondria that produce energy through aerobic respiration, and with a whole suite of other complex internal structures. The origin of eukaryotes is thought to have involved endosymbiosis, where one prokaryotic cell engulfed another, and the engulfed cell became an organelle. Understanding when this happened is crucial for understanding the trajectory of life's evolution. Microbial ecosystems in the late Archean would have been increasingly complex. Stromatolites, built by diverse communities of microorganisms, were common in shallow marine environments. Different metabolic types coexisted: photosynthetic organisms producing oxygen or other compounds, aerobic organisms beginning to utilize the limited oxygen available, anaerobic organisms thriving in oxygen-free niches, methanogens producing methane, sulfate reducers processing sulfur compounds, and many others. The ecological food webs were becoming more intricate, with primary producers, consumers, and decomposers all playing their roles. The transition from Archean to Proterozoic at 2,500,000,000 years ago is not marked by a dramatic event visible in the rock record, unlike some later boundaries. Instead, it is a somewhat arbitrary division placed at a convenient round number. However, this boundary falls in the midst of one of Earth's most significant transitions, the Great Oxygenation Event. While the full oxygenation of the atmosphere would unfold over the first few 100,000,000 years of the Proterozoic, the seeds were sown in the Archean. The biological machinery was in place, the chemical prerequisites were met, and the planet was poised for transformation. As we bid farewell to the Archean Eon, we can reflect on the extraordinary journey Earth had taken. From a molten, impact-battered wasteland at the beginning, it had become a planet with stable continents, extensive oceans, a regulated atmosphere, and abundant life. The Archean was the eon when Earth became truly planetary, when it developed the features that would define it for the rest of its history. The stage was set, the actors were in place, and the drama of Earth's oxygenation and the eventual evolution of complex life was about to begin. Standing here, 4 billion years after the Archean's dawn and 2.5 billion years after its close, we might wonder what relevance this ancient eon has to our modern world. The answer is everything. The Archean Eon was not merely a prelude to later events, but the foundation upon which all subsequent history was built. Its legacy surrounds us, beneath our feet, in the air we breathe, in the diversity of life we see, and in the very habitability of our planet. The most direct legacy of the Archean is literal: the ancient cratons that form the cores of modern continents. Every continent contains Archean rocks, and these rocks compose the oldest, most stable portions of the continental crust. The Canadian Shield, the Yilgarn Craton of Australia, the Karpval Craton of Southern Africa, the Siberian Craton, the Indian Shield, and the São Francisco Craton of Brazil all contain substantial Archean components. When we walk on these ancient terrains, we are walking on rocks that formed when Earth was young, rocks that have witnessed the entire subsequent history of our planet. These Archean rocks are not merely historical curiosities. They are economically vital, hosting many of the world's most valuable mineral deposits. The gold deposits of the Witwatersrand Basin in South Africa, the nickel deposits of Kambalda in Australia, the iron ore of the Hamersley Basin, the copper and zinc of the Abitibi Greenstone Belt in Canada. All these trace their origin to Archean geological processes. Mining these deposits, we are extracting wealth that was concentrated billions of years ago by volcanic processes, hydrothermal circulation, and the settling of heavy minerals from magmas in a hotter, more geologically active Earth. The Archean also established the basic geochemical structure of Earth's crust and mantle. The formation of continental crust through the extraction of silica-rich material from the mantle depleted the mantle in certain incompatible elements, while enriching the crust in these same elements. This chemical differentiation has affected all subsequent volcanism and crustal formation. The thick lithospheric roots beneath cratons, formed in the Archean and still present today, influence mantle convection patterns, and may help determine where new plate boundaries form and where old ones persist. In terms of atmospheric evolution, the Archean set Earth on a trajectory toward an oxygen-rich atmosphere, though the full realization of this trajectory would occur in the Proterozoic. The evolution of oxygenic photosynthesis during the Archean was the pivotal innovation that would eventually lead to the modern oxygen-rich atmosphere. Without this innovation, Earth might have remained an anaerobic world, capable of supporting only microbial life, never evolving the complex organisms that require oxygen for their metabolism. The biological legacy of the Archean is equally profound. All life on Earth today descends from organisms that evolved during the Archean or earlier. The basic biochemical machinery of life, the genetic code, the fundamental metabolic pathways, all these were established by Archean organisms. Many of the metabolic innovations that occurred during the Archean, including photosynthesis, nitrogen fixation, methanogenesis, and sulfur metabolism, are still used by organisms today, often in remarkably similar forms. The Archean experience also taught us crucial lessons about how planets evolve and what makes them habitable. The interplay between geological and biological processes, evident throughout the Archean, demonstrates that planets are complex systems where the abiotic and biotic components influence each other in intricate feedback loops. Life did not merely adapt to its environment during the Archean. It changed that environment, altering atmospheric chemistry, ocean chemistry, and even the types of rocks that could form. This principle of life as a planetary force, sometimes called the Gaia hypothesis in more developed forms, was demonstrated first in the Archean. For astrobiology, the search for life beyond Earth, the Archean provides important analogies and lessons. When we search for life on Mars, on the icy moons of Jupiter and Saturn, or on exoplanets orbiting distant stars, we often look for conditions similar to those that existed on Earth when life arose and diversified. The Archean teaches us that life can thrive in the absence of oxygen, that it can influence planetary chemistry profoundly, even when present only as simple microorganisms, and that it can persist through environmental changes, including major shifts in atmospheric and oceanic chemistry. The Archean also reminds us of the importance of deep time. The Eon lasted 1.5 billion years, longer than the entire subsequent Proterozoic and Phanerozoic eons combined. During this vast span, changes occurred that seem rapid from a geological perspective, but that unfolded over timescales incomprehensible to human experience. The transition from a planet without stable continents to one with substantial land masses, from a planet without oxygen to one beginning to oxygenate, from a planet with simple chemistry to one with complex ecosystems. All these took hundreds of millions to billions of years. This perspective on timescales is crucial as we think about modern environmental changes. The relatively rapid changes we are causing to Earth's atmosphere, oceans, and ecosystems, occurring over decades to centuries rather than millions of years, are unprecedented in their speed. The Archean teaches us that planetary systems can absorb and respond to changes, but that such responses operate on geological timescales. The oxygen crisis that anaerobic organisms faced as cyanobacteria proliferated unfolded over hundreds of millions of years, giving organisms time to evolve tolerance or retreat to anoxic refugia. Modern organisms, facing changes occurring thousands of times faster, have far less time to adapt. As we contemplate the future, the Archean also offers a salutary reminder of impermanence. The world of the Archean, with its grey-green seas, orange skies, stromatolite-covered coastlines, and absence of complex life, seems utterly alien to us. Yet it was the normal state of Earth for 1.5 billion years, far longer than Earth has existed in anything like its modern condition. The Earth we know, with its oxygen-rich atmosphere, its abundant complex life, its familiar geology and climate, is itself transient. On geological timescales, today's Earth is as temporary as the Archean Earth was. This should inspire both humility and wonder. Humility because we are part of a planetary story vastly older and larger than ourselves, one that will continue long after humanity is gone. Wonder because we have the privilege to study this story, to decode the messages preserved in ancient rocks, to reconstruct the alien world of the Archean and understand how it transformed into the world we inhabit. In studying the Archean, we are not merely satisfying curiosity about the past. We are understanding the fundamental processes that made our existence possible, the deep history that connects us to the origin of our planet and the origin of life itself. So the next time you encounter Archean rocks, whether in a museum, in a rock outcrop, or in a photograph from some remote corner of the world, pause for a moment. You are looking at material that formed when Earth was young, when the continents were first being born, when life was learning to photosynthesize, when the future that would become our present was just beginning to unfold. These rocks are time capsules, messengers from an alien world that was nonetheless our world, the Earth of 4 billion years ago. They remind us of where we came from. They help us understand where we are, and they provide crucial insights for thinking about where we and the planet might be going. If you enjoyed this deep dive into Earth's ancient past, please consider giving this video a like and subscribing to the channel. Your support helps me continue creating detailed, carefully researched content about the fascinating history of our planet and the cosmos beyond. The journey through deep time continues, and I'd love to have you along for future explorations into the geological, biological, and astronomical wonders that shaped our world. Thank you for watching, and until next time, keep looking back to understand our present.